Welcome to the flock. Let's dive into Gay-Lussacs law relating pressure and temperature by solving problems such as this. Before we can solve the problem, we first need to understand the equation setup. For Gay-Lussacs law, we're assuming that if the amount, the N or the moles of the gas, and the volume of the gas V remain constant, then we can say that the pressure exerted by the gas on its container will directly affect the temperature. And remember, this is temperature in Kelvin, not degrees Celsius, not degrees Fahrenheit. This relationship between pressure and temperature is a direct one, meaning that if the pressure goes up, the temperature went up. If the temperature goes down, then the pressure will also go down. And anytime we have a direct relationship with variables, or a direct proportionality, that's what that little fish symbol means, we have a mathematical setup that involves division. So here, for Gay-Lussacs law, we're going to have our initial pressure divided by our initial temperature set equal or equivalent to our final pressure and our final temperature in Kelvin. So basically, if I increase the temperature of this pot from low to high, we can also see that the pressure is moving up on the little indicator there. If I go back down and decrease the temperature, my pressure also decreases. Now that you have an idea of what Gay-Lussacs law is, let's go ahead and solve this problem involving cannons. Awesome. When gunpowder burns, it creates a lot of superheated gas. And since it creates a lot of gas, it applies perfectly to our gas laws, of course. The high pressure of that hot gas, because remember, according to KMT, temperature increases the average kinetic energy of those gas molecules, therefore they move faster, hit the walls of their container faster, and cause increased pressure. And that increased pressure is the force needed in order to launch a cannonball out of a cannon. So let's solve this real-world problem. These are actual values for cannonball firing. In order to fire a cannonball, we need about 100 psi of pressure required. And now that's in comparison to the normal sea level pressure of 1 atm. If we assume that the cannon is at room temperature before it's fired, that's the 23 degrees Celsius, what would be the temperature just before that cannonball literally shoots out of the cannon? Before we can plug and chug into our P1 over T1 equals P2 over T2 equation, we have a few conundrums that we need to fix here. The first being that these two units don't match. Anytime we plug in pressures or temperatures into an equation, we need the units to match in order for them to cancel out and in order for us to actually solve our math correctly. Here, if we tried plugging in 100 psi and 1 atm, those two units are not equivalent. We need the same units in order to plug and chug. The other thing is that this temperature is in degrees Celsius. In order to use it in Gay-Lussacs law, we need it to be in Kelvin. So let's do some conversions first before we can plug and chug. From my gas terms and units video in the past, we learned that 14.69 psi is equivalent to 1 atm. This is the conversion factor we can use in order to convert this into atm or this into psi, whichever you prefer. Either way, it's not specifying what the pressure has to be in, so you can just do whatever you're more comfortable with. In this case, I'm going to convert the 100 psi over to atm. We're going to start with our magical line to freedom. 100 psi is our given, and we're trying to figure out what that is in atms. We know that 1 atm is equivalent to 14.69 psi. I put the psi on the bottom so that our psi units can cancel and we will be left with atms, which is the goal. So all I have to do now is multiply 100 by 1 and divide that by 14.69. When I do so, I yield a value of 6.8 atms. Great, now the next thing I need to do is convert my 23 degrees Celsius into Kelvin. The way we do that is by adding 273 to any degrees Celsius in order to find Kelvin. And when we do so, we see that it ends up being 296 Kelvin. Now we just need to figure out which one is our P1, T1, P2, T2. We're saying that initially our normal ambient room temperature is 1 atm, so that's going to be our initial pressure. Our final pressure, right before the cannonball fires, is going to be the 6.8 atms that we calculated. The initial room temperature is 296 Kelvin, and we're trying to figure out what T2 is. Excellent, now it's just a matter of plug and chug into our Gay-Lussac equation. We'll have 1 atm over 296K set equal to 6.8 atms over x. That's what we're solving for. On this side, my 1 divided by 296 yields a value of 0.00337, still set equal to 6.8 over x. In order to get x out of the denominator, I'm going to multiply each side by x. Now all I have to do is divide off the 0.00337 from both sides to get x alone. And I end up with a T2 of 2012.8 Kelvin. Now that's really, really hot. Just how hot? Let's convert it back to degrees Celsius to get a better idea. In order to calculate for the degrees Celsius, we just need to subtract over our 273 from both sides. And we end up with degrees Celsius of 1,739.8 degrees Celsius. That is really, really hot. For reference, water boils at 100 degrees Celsius. Using that same logic we just talked about for a cannonball, let's think about how a bullet fires from a gun, chemically. If you're unfamiliar with bullets, know that the golden casing here at the bottom is what contains all the gunpowder. That's the flammable explosive stuff. The copper tip, that's this part right here at the very top, is what actually flies out of the bullet as the projectile. And the round circle on the bottom of the casing, or on the butt right here, that's where the firing pin in the gun hits it in order to ignite a spark in the gunpowder and cause the explosion to happen. Alright, pause the video here and think about how you would explain, using Gay-Lussacs law, how a bullet fires from a gun. We know that when the firing pin hits that butt on the casing, it ignites a spark on the gunpowder, which causes the temperature to increase. If the temperature increases, we know that the pressure also increases. With the increased pressure of the gas molecules on the inside of the barrel, that's enough force to propel the bullet, or the copper tip, out of the gun barrel and as a projectile into space. Gas laws are everywhere. Now that you've seen me do a calculation, go ahead and pause the video here so that you can give it a try. Now you might be asking yourself, where on earth did I get this 760 millimeters of mercury to 1 atm conversion factor? If you don't recall where that pressure conversion factor comes from, please check out my previous video on gas terms and units, linked in the description below. Alright, so hopefully you got 0.239 atmospheres of pressure as our P2 answer. Check your understanding here. We know that Gay-Lussacs law is that as pressure increases, temperature should also increase, and vice versa. Here in this problem, we saw that the temperature did in fact increase from 77 to 298, and our pressure also increased from 0.0618 to the 0.239 atms. So we know we must have done this calculation correctly. Please keep in mind that if you're doing a gas law experiment and you happen to plot pressure on the y-axis and temperature in Kelvin on the x-axis, and you end up with this straight line, that's indicative of a direct relationship and would indicate that Gay-Lussacs law is being followed here. Also keep in mind that this law can only work if we assume that the volume is constant and that the moles of the gas present remain constant as well. Let me show you Gay-Lussacs law in action using a candle and water and a beaker. As I do the experiment, think about what's happening with the atoms and the molecules, the pressure, the volume, and the temperature in the entire experimental setup. How to make water defy gravity in 3 easy steps. Step 1. Take food dye water and pour it onto a level flat plate. In the middle of this plate, I have 3 candles. Light them. With a large enough container, like a 1,000 milliliter beaker, cover the candles. As you can see, the water got drawn up into the beaker. This is due to Gay-Lussacs gas law in chemistry, which relates pressure and temperature. When we light the candles, the temperature goes up, and the gas molecules inside the chamber move faster due to the increased temperature. When we put the beaker over the top, that increases the pressure because now the gas is moving really fast in a confined space. Then once the candles extinguish, the temperature goes down, causing the gas molecules to move slower and the pressure to go down. When the pressure goes down, the water has to go somewhere, and it goes up, creating a literal chemistry vacuum chamber. Before moving onwards and upwards, make sure that you test yourself before you wreck yourself on these Gay-Lussac concepts. See if you can answer these 2 questions. And let me know, is the temperature of 527 degrees Celsius on the planet Venus sufficient to make a car tire explode? Tell me in the comments below. In this lesson, we talked about Gay-Lussacs Law, which relates pressure and temperature via a direct relationship with P1 divided by T1 set equal to P2 divided by T2. Remember, those temperatures are always in Kelvin, and always make sure that your pressure units match each other. We know that this concept can only hold true if the moles of the gas and the volume are assumed to remain constant, and we know experimentally that graphing pressure versus temperature in Kelvin should yield a direct line relationship. Please give this video a quacksa, and please subscribe to the Duck.
No ducks, no glory.